Hello, Accelerated Chemistry. This is Ms. Crisipoli, and this is your Chapter 8, Section 4 video notes all over polar bonds and molecules. So let's first talk about the types of covalent bonds that you can have. So covalent bonds differ in terms of how the bonded atoms will share their electrons. And the character of the molecule depends on the kind and number of atoms that join them together. So in these features, in turn, will determine the molecular properties of the compound. So let's talk about, there's two types of covalent bonds. There's nonpolar covalent or polar covalent bonds. So a nonpolar covalent bond is when you have an equal sharing of electrons. So the two bonding atoms are going to have similar electronegativities, and they're going to result in a neutral molecule. And it's usually going to be between identical atoms. So an example would be Cl2. The second type of covalent bond is a polar covalent bond. This is when you have an unequal sharing of electrons, and one of the atoms is going to have a higher electronegativity, thus having a stronger attraction for those electrons. So one atom is slightly negative and the other one's going to be slightly positive. An example for this would be HCl, and when we have an HCl molecule that has a slightly positive side and a slightly negative side, we call this a dipole. When we look at the type of covalent bonds, if you have an equal sharing of electrons, remember it's going to be a nonpolar covalent bond. And if you have an unequal sharing of electrons, you are going to have a polar covalent bond. So you can determine the type of bond that you have based on using the electronegativity differences. Remember, electronegativities range from 0 to 4. Fluorine is going to have the highest. So when you look at the difference in the two elements that form the bond and take the difference in their electronegativities, you can determine what type of bond character the bond's going to have, either nonpolar covalent, polar covalent, or ionic. So let's look at an example. What type of bond exists between a hydrogen atom and an oxygen atom? So if we look at hydrogen and oxygen, hydrogen's electronegativity is 2.2. Oxygen's electronegativity is 3.4. So when we subtract those, we get a 1.2. It's going to be absolute values, so don't worry about your negatives. And that is a polar covalent bond. And that should make sense because oxygen is more electronegative, so it's going to pull the electrons more towards it. What if we're looking at the difference between a hydrogen and a carbon atom? Hydrogen's electronegativity is 2.2. Carbon's electronegativity is 2.6, and that has an electronegativity difference of 0.4, so that is considered to be a nonpolar covalent bond. So what about if we're looking at an oxygen and oxygen atom? So we have oxygen and oxygen, so 3.4 minus 3.4, and that's going to be 0, and we have a nonpolar covalent bond. Remember, what does nonpolar covalent bond mean? It means that we are going to be sharing those electrons between the two oxygens evenly. And then what happens between a sodium and a chlorine atom? So we have Na, which has an electronegativity of 0.9. We have Cl that has an electronegativity of 3.2. When we subtract those, we get 2.3. That's above 1.7, so that element has an ionic bond character. And that should make sense to you because sodium is a metal, chlorine is a nonmetal, and in fact, that is an ionic bond. So now let's talk about molecular polarity. There are two types of electron domains: bonding pairs, which are going to be the electrons that form the bonds in the molecule, and then the lone pairs. Those are the dots that are going to be not part of the bond. So molecular polarity is going to depend on two things: the bonding polarity, so the polarity between the bonds, and also the shape of the molecule. So if the shape is symmetrical, that means all on the same side, all the elements around the central atom are the same, or it's going to be asymmetrical, meaning that everything is not going to be the same on all the sides when you look at the central atom. So remember, shape is caused by the VSEPR model, which is the valence shell electron pair repulsion model. And so remember that valence electrons are arranged as far from one another as possible to minimize the repulsion between them. So what does that mean? That means that if you have a polar molecule, and it's going to be polar if it contains polar bonds and is asymmetrical, so not the same on all sides. And if there are lone pairs on the central atom, then the molecule is automatically polar. So when we're looking at nonpolar molecules, if a molecule is nonpolar, it contains only nonpolar bonds, and is symmetrical or the same on all sides of the molecule. So that talks about bond polarity, molecular polarity. Now let's talk about attraction between molecules. So we have what are called intermolecular attractions. And these are weak forces of attraction that happen between molecules. And they're responsible for determining the state of matter a molecular compound is going to be at room temperature, or at any temperature for that matter. And remember, a molecular compound is a compound that contains covalent bonds. So there's 4 types of intermolecular forces: ion-dipole, dipole-dipole, London dispersion forces, which you'll hear me refer to in class as LDFs, and hydrogen bonding. So let's start off with ion-dipole. Ion-dipole interactions occur between an ion and a molecule that is polar. So what happens is that there's going to be an electrostatic attraction between the ion and the oppositely charged end of a polar molecule. And this is the strongest of the intermolecular forces. So what does that look like? So when we're looking at water and we look at salt dissolving in water, there's actually an ion-dipole interaction. So if you look at the left, the chlorine atom is negatively charged, we know that. And water actually has a positive end where the hydrogens are and a negative end where the oxygen is, because it has an uneven distribution of electrons. So it's a polar molecule. The positive side of the water molecules, the hydrogens, are going to be attracted to that negative Cl. The opposite is true for the Na+, and the O, that is an oxygen. The O in the water molecule, the oxygen, is going to be negatively charged, and that's going to be attracted to the positive Na+ ion. So let's talk about the second one, which is dipole-dipole. This occurs between 2 molecules that are polar. So there's an electrical attraction between oppositely charged regions of the polar molecule. And this is similar to, but much weaker than, what we see in ionic bonds, or the ion-dipole interaction. So this would be what it would look like. So we have a polar molecule here, and we have multiples of that polar molecule. And you can see how the positive side of one end of the molecule is going to be attracted to the negative side of the adjacent molecules. And that's how those things stay in place or stay close to each other when they're in a solid, liquid, or gas phase. The next one we're going to talk about is London dispersion forces, or LDFs. They're the weakest of all the intermolecular forces. The strength of the London dispersion forces increases as the numbers of electrons in the molecule increase. So basically what happens is that you will have electron clouds around your atoms. So when you have an electron cloud around one side of an atom and it gets close to another atom, it's going to shift the electrons away because there's going to be repulsion between those electrons. So you're going to create what we call a temporary dipole moment, which means that that molecule is going to get a partial negative, partial positive side, and then the other molecule is going to have a partial negative, partial positive side, and then the opposite sides are going to be attracted to each other. So that's what this looks like here. So we have an uneven distribution of electrons here, and that attractive force between them is going to be your London dispersion force. So when we're talking about London dispersion forces, if we look at group 17, for example, our strength is going to increase because the molecule gets bigger as we go down group 17. We're adding more electrons into more energy levels outside the nucleus. So the molecule is going to physically get bigger, which means that its London dispersion forces are also going to get larger. Let's talk about hydrogen bonding. Hydrogen bonding is stronger than London dispersion and dipole-dipole interactions, but they're weaker than ion-dipole. And this occurs between hydrogen and one atom of nitrogen, oxygen, or fluorine on an adjacent atom. So remember, hydrogen bonding is fun, F-O-N, only occurs with fluorine, oxygen, and nitrogen. And that's what this would look like. So in water, we actually see hydrogen bonding because we have the hydrogen interacting with the negative oxygen of the next molecule of water. So now we've talked about intermolecular forces, we've talked about molecular polarity. Now let's talk about what that does with their properties. So at room temperature, some compounds are gases, some are liquids, and some are solids. And the physical properties will be dependent upon what kind of bonding it has, either ionic or covalent. So the diversity of physical properties among covalent compounds is mainly because of their intermolecular attractions, the attractions between the molecules. So the melting points and boiling points of most compounds are composed of molecules are low compared to those of ionic compounds because they have weaker attractive forces between them. In most solids are formed by molecules, only the weak attractions between the molecules need to be broken. So a few solids that consist as molecules that do not melt until temperatures reach 1,000 degrees or higher are called network solids. These are substances that are very stable, and they can occur when you have atoms that are covalently bonded to each other. And the melting of a network solid would require breaking covalent bonds throughout the solid. So that is something different than the attraction between the molecules. An example of a network solid is diamond. Each carbon atom is covalently bonded to 4 other carbon atoms, which makes carbon the strongest substance on the planet. Diamond does not melt. It will vaporize, which means that it goes directly from a solid to a gas at 3,500 degrees Celsius and above. And so if we were to look at everything that we just talked about, and if we were to look at intermolecular attractions, molecular properties, this would be a great chart to write down in your notes so that you compare ionic compounds to molecular compounds, especially since your midterm is coming up next week. And as always, all of the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the textbook Resources CD and pearsonchem.com. Have a good night. See you tomorrow.